Take a slow breath in and let it go. Tonight, we're going to drift far beyond the noise of the day, past city lights and daily thoughts, and gently lift our attention toward the quiet glow of the stars. Above us, whether we notice them or not, billions of stars shine patiently in the night sky. They have done so for millions, even billions of years. They ask nothing from us. They simply exist calmly and beautifully. Welcome to this peaceful journey through 80 star facts, shared slowly and softly, designed to help your mind unwind and your body rest. You don't need to remember every detail. You don't need to stay awake for all of it. If your thoughts begin to wander, that's perfectly fine. Let them wander among the stars. If you find comfort in calm educational stories like this, you're warmly invited to like and subscribe, but only if it truly feels right for you. And if you're awake enough, you can share where you're listening from tonight, your country, your city, and the time, knowing that people all around the world may be listening alongside you under the same sky. Now, let's begin gently. When we look up at the night sky, it can feel timeless. Yet every star we see has a story, a beginning, a long life, and eventually an ending. Stars are not static points of light. They are dynamic, powerful objects made mostly of hydrogen and helium, slowly transforming energy deep within their cores. The soft light reaching your eyes tonight may have traveled for years, decades, or even centuries before arriving. One of the most calming thoughts about stars is this: starlight is a form of history. When you see a star, you are seeing it as it once was, not as it is right now. Some stars you see may no longer exist, yet their light continues its quiet journey through space. In this way, the night sky is like a living museum, preserving moments from the distant past. Stars are born inside vast clouds of gas and dust called nebulae. These clouds drift silently through galaxies, shaped by gravity and time. Over thousands or millions of years, small regions within a nebula begin to collapse under their own weight. As the material gathers, it warms slowly and steadily. Eventually, when the core becomes hot enough, nuclear fusion begins. A star is born, not with a sudden explosion, but with a gradual ignition, like a soft, cosmic dawn. Our own sun is one such star, though it feels special because it is close to us. In reality, it is an average-sized star among hundreds of billions in the Milky Way galaxy. Yet, without it, life on Earth would not exist. Its steady energy warms oceans, fuels weather, supports ecosystems, and quietly makes our daily lives possible. Thinking of the sun as a star helps us feel connected to the larger universe, reminding us that Earth is part of a much greater cosmic story. Stars come in many sizes and colors. Some are small and cool, glowing softly red. Others are massive and hot, shining blue or white. The color of a star tells astronomers about its temperature. Red stars are cooler, while blue stars burn extremely hot and live much shorter lives. Even this has a calming lesson. In the universe, faster and brighter often means shorter, while slower and steadier can last far longer. Some stars live for only a few million years, burning through their fuel quickly. Others, especially small, red dwarf stars, can shine quietly for trillions of years, longer than the current age of the universe. These stars are patient by nature, changing so slowly that, from our perspective, they seem eternal. The distances between stars are immense. Even within our own galaxy, stars are separated by vast stretches of near-empty space. This means that collisions between stars are incredibly rare. Space, despite its dramatic reputation, is mostly calm and quiet. It is this spaciousness that gives the universe its peaceful character. For centuries, humans have looked to the stars for guidance, inspiration, and comfort. Ancient travelers used them for navigation. Farmers watched them to mark the seasons. Cultures across the world wove star patterns into myths, legends, and stories, passing them down through generations. Even today, stargazing remains a powerful way to feel grounded and small in the best possible way. The night sky can also feel deeply personal. No matter where you are on Earth, the stars above you are part of a shared human experience. People in distant countries, on remote islands, and in quiet rural towns all look up at the same sky. This shared view creates a subtle sense of connection, even across great distances. As we continue, we'll explore how stars live and change, how they form groups and clusters, how they influence planets, and how astronomers study them with modern technology. We'll move slowly, fact by fact, allowing each idea to settle gently before drifting on to the next. There's no rush. The stars have waited billions of years. They can wait a little longer with you. You're breathing slow. Let your shoulders relax and allow your attention to float upward toward the quiet glow above. As your breathing settles into a slower rhythm, let's drift deeper into the quiet places where stars begin their lives. Long before a star shines, long before it warms planets or lights up a night sky, it exists as a possibility hidden inside vast, silent clouds floating through space. These clouds are called nebulae. Nebulae are enormous regions made of gas and dust, stretching across distances so large that even light can take years to cross them. They are among the calmest structures in the universe, drifting slowly within galaxies like the Milky Way. Inside them, hydrogen gas dominates, mixed with helium and tiny grains of cosmic dust. From afar, nebulae can appear like soft, glowing mist, tinted pink, blue, or violet by nearby starlight. Despite their gentle appearance, nebulae are places of quiet transformation. Over immense periods of time, gravity begins to pull parts of a nebula inward. This process is unhurried. There is no sudden rush, no sharp moment when everything changes. Instead, gravity works patiently, drawing gas closer and closer together. As the material gathers, it forms denser regions called protostars. These are not yet true stars, but they are on the path to becoming one. Inside a protostar, pressure and temperature begin to rise slowly. Energy builds, but it is still contained, still waiting. This phase can last hundreds of thousands of years or longer. One calming truth about star formation is how slow and forgiving it is. Nothing happens instantly. There is time for balance to form, time for forces to settle. In a universe often imagined as violent and chaotic, star birth reminds us that creation can be gradual and gentle. Eventually, if the growing core becomes hot enough, about 10 million degrees Celsius, nuclear fusion begins. Hydrogen atoms start to fuse into helium, releasing energy. This moment marks the birth of a true star. Light and heat begin to flow outward, pushing back against gravity. A balance forms between inward pull and outward pressure, and the star enters a long, stable phase of its life. Most stars spend the majority of their existence in this balanced state, known as the main sequence. Our Sun is currently in this stage, calmly converting hydrogen into energy day after day for billions of years. This steady phase is why stars feel reliable and comforting from Earth. They don't flicker or surge dramatically. They shine with consistency. Nebulae don't disappear when stars form. In fact, newborn stars often illuminate the clouds around them, causing the surrounding gas to glow softly. These glowing nebulae become some of the most beautiful sights in astronomy, captured by telescopes and admired for their peaceful, dreamlike appearance. Some nebulae are known as stellar nurseries because they contain regions where many stars are forming at once. The Orion Nebula, visible from Earth with the naked eye under dark skies, is one such place. Within it, thousands of young stars are slowly emerging, each with its own future. Not all nebulae form stars at the same pace. Some regions remain calm and inactive for millions of years, while others begin forming stars after being disturbed by nearby events, such as the shock wave from a distant supernova. Even then, the response is slow, like ripples spreading gently across a quiet pond. There is something deeply soothing about knowing that stars, which feel so permanent and bright, begin their lives in darkness and quiet. Before any light shines, there is patience. Before any brilliance, there is stillness. Nebulae also remind us that creation and recycling are connected in the universe. The gas and dust inside them often come from older stars that ended their lives long ago. When those stars released their material back into space, they provided the ingredients for new stars to form. In this way, the universe reuses its material, shaping new light from old remnants. This cycle has repeated countless times over billions of years. The atoms in your body were once part of stars, forged in stellar cores or spread through space by stellar winds. When you look up at the sky, you are not separate from it. You are made from the same cosmic ingredients. Star birth also influences the formation of planets. As a new star forms, a flat disk of gas and dust often spins around it. Within this disk, particles collide gently, sticking together over time. Slowly, these clumps grow larger, becoming planetesimals, and eventually, planets. Entire solar systems can emerge from the leftover material of star formation. This means that calm, steady processes shape not only stars, but also worlds. Planets like Earth form, not from chaos, but from countless small interactions happening quietly over millions of years. Some stars form alone, while others are born in groups called star clusters. In these clusters, stars begin their lives close together, sharing similar ages and compositions. Over time, many clusters drift apart as stars slowly move through the galaxy, carrying their shared origins with them. Even after leaving their birthplaces, stars continue their gentle journey around the center of their galaxy. Our Sun, for example, orbits the center of the Milky Way, completing one slow revolution roughly every 225 million years. During that time, it passes through regions rich with nebulae and other stars, always moving, always part of a larger flow. As we rest with these thoughts, it becomes easier to let go of urgency. The universe does not hurry. It unfolds. Stars are born, shine, and change on timescales far beyond daily worries. When we align our thoughts with this rhythm, even briefly, the mind can soften. As we continue drifting through the quiet universe, let's follow a star after its birth, once it has settled into a long and steady rhythm. This stage, known as the main sequence, is where stars spend most of their lives. It is also where they are at their calmest, shining with a dependable glow that can last for millions or even billions of years. A star in a main sequence is balanced. Gravity pulls inward, trying to compress the star, while energy from nuclear fusion pushes outward. These two forces meet in harmony, creating stability. This balance allows stars to shine consistently, without dramatic changes, for most of their existence. The length of this phase depends largely on the star's mass. Smaller stars, called red dwarfs, burn their fuel very slowly. They sip hydrogen gently, conserving energy. Some red dwarfs can remain in the main sequence for trillions of years, far longer than the current age of the universe. These stars glow dimly but steadily, like tiny embers scattered across the galaxy. Larger stars, on the other hand, burn much hotter and faster. Massive blue stars consume their fuel quickly, shining brilliantly but briefly. Some may only remain stable for a few million years before beginning to change. Even so, during their main sequence phase, they still follow the same calm balance of forces. Our Sun is a medium-sized star, and it has been shining steadily for about 4.6 billion years. It has enough hydrogen fuel to continue this gentle process for another 5 billion years or more. This long-term stability is one of the reasons life was able to develop on Earth. Reliable sunlight allowed climates to settle, oceans to remain liquid, and ecosystems to evolve slowly over time. Stars shine because of nuclear fusion in their cores. In most main sequence stars, hydrogen atoms fuse together to form helium. This process releases energy in the form of light and heat. The energy takes a long time to travel from the core to the surface, sometimes hundreds of thousands of years, moving gradually through layers of plasma before finally escaping into space. When you see starlight in the night sky, you are witnessing energy that began its journey deep inside a star long ago. That light traveled slowly through the star, then crossed vast distances of space before finally reaching your eyes. There is something soothing in knowing that even light moves patiently. Stars come in many colors, and these colors reveal important information. Blue stars are hotter, burning at higher temperatures. White and yellow stars, like the sun, are moderately hot. Orange and red stars are cooler, though still incredibly warm by everyday standards. Color, temperature, and brightness are closely connected, forming patterns that astronomers use to understand stellar life cycles. These patterns are often displayed on a diagram called the Hertzsprung-Russell diagram, which organizes stars by brightness and temperature. It shows that stars are not random points of light, but part of an orderly system. This sense of structure adds to the calming beauty of astronomy. The universe follows rules, and stars obey them quietly. Stars also rotate, spinning slowly on their axes. The speed of rotation varies, with some stars turning gently, while others spin more rapidly. This rotation can influence magnetic fields and surface activity, such as starspots, which are cooler regions similar to sunspots on our Sun. Our Sun experiences an 11-year cycle of magnetic activity, during which sunspots increase and decrease. Even this activity follows a predictable pattern. While solar flares and eruptions can occur, they are part of a larger, repeating rhythm that has continued for billions of years. Stars are not isolated from their surroundings. They exist within galaxies filled with gas, dust, and other stars. As they move through the galaxy, they interact subtly with this environment. Some stars pass near nebulae, while others drift through relatively empty regions of space. Many stars exist in systems with one or more companions. Binary stars, where two stars orbit each other, are quite common. In these systems, the stars move in slow, graceful paths, bound by gravity. Some binary systems are so close that the stars exchange material, while others remain far apart, barely influencing each other. There are also star clusters, where groups of stars formed together remain loosely bound. Open clusters contain young stars that still travel together, while globular clusters are ancient collections of hundreds of thousands of stars, orbiting galaxies like quiet, spherical islands of light. Globular clusters are among the oldest structures in the universe. Some are over 12 billion years old, nearly as old as the Milky Way itself. Inside them, stars shine calmly, having lived through almost the entire history of the cosmos. Stars also contribute to the larger economy of matter and energy in the universe. Through stellar winds, they slowly release particles into space. Over time, this material enriches the interstellar medium, providing raw ingredients for future star formation. Even during their stable phases, stars gently give back to their surroundings. In a way, stars are generous. They shine without expectation, releasing energy freely into space. Planets absorb this energy, climates form, and life may emerge. Yet, the star itself continues its steady fusion, unaware of who benefits from its light. As we relax with these ideas, it becomes easier to see stars not as distant objects, but as participants in a shared cosmic story. Their long lives mirror patience, consistency, and quiet endurance. They remind us that stability can last a very long time, and that not everything needs to change quickly. As we continue our gentle journey through the night sky, let's remain calm and curious as we explore what happens when a star slowly begins to change. There is no sudden rush in this process. Stellar evolution unfolds gradually over spans of time so long that they feel almost eternal. A star begins to change when the hydrogen fuel in its core starts to run low. For millions or billions of years, hydrogen fusion provided a steady source of energy, keeping gravity and outward pressure in balance. But eventually, even vast reserves of hydrogen are not infinite. When the core hydrogen is mostly used up, that delicate balance begins to shift. Gravity, patient and persistent, starts to pull the star inward. The core slowly contracts and becomes hotter. This rise in temperature triggers new reactions, even before hydrogen fusion fully stops. Meanwhile, the outer layers of the star respond by expanding gently outward. For medium-sized stars like our Sun, this transition turns the star into what astronomers call a red giant. The star grows much larger, its surface cooling slightly as it expands. Despite the cooler surface, the star becomes brighter overall because of its increased size. A red giant can grow so large that it would engulf nearby planets if placed where our Sun is now. This transformation is not violent. It is slow and graceful, like a deep breath taken over millions of years. From a distance, the star continues to glow calmly, though its color shifts toward warm shades of orange and red. Inside the expanding star, new processes begin. The core becomes hot enough to fuse helium atoms into heavier elements like carbon and oxygen. This helium fusion releases energy, briefly restoring balance once again. For stars of moderate size, this phase brings a new kind of stability, though it does not last as long as the hydrogen burning stage. Smaller stars, especially red dwarfs, follow a different path. Because they burn their fuel so slowly and mix their material efficiently, they may never become red giants at all. Instead, they gradually use up their hydrogen over trillions of years, slowly dimming and cooling. Since the universe is not yet old enough, no red dwarf has completed this journey yet. These stars remain quietly shining, reminders of the universe's patience. More massive stars experience more dramatic changes. When their core hydrogen runs out, gravity causes rapid contraction and intense heating. These stars expand into supergiants, becoming enormous and luminous. Their outer layers swell far beyond their original size, glowing brightly across great distances. Inside massive stars, fusion continues beyond helium. As temperatures rise, heavier elements begin to form in layers like the rings of an onion. Carbon, neon, oxygen, and silicon all fuse in sequence, each stage lasting shorter than the one before. Yet even here, the process remains governed by natural laws, unfolding step. The color of a star during these later stages can vary. Red supergiants glow softly in reddish hues, while blue supergiants remain hot and intense. These colors help astronomers understand what is happening deep within the star, even from far away. Throughout these changes, stars continue to influence their surroundings. Their expanded size and increased brightness affect nearby space, warming planets and shaping interstellar clouds. In distant galaxies, supergiant stars can be seen across vast cosmic distances, contributing to the beauty and structure of the universe. Stars in this phase also shed material more actively. Stellar winds grow stronger, carrying gas and dust away from the star. This material drifts into space, enriching the galaxy with elements that will one day become part of new stars, planets, and perhaps living worlds. There is something comforting in knowing that change does not mean destruction. For stars, change is simply another stage in a long, meaningful existence. Each phase builds upon the last, contributing to the ongoing cycle of creation in the cosmos. From a human perspective, these transformations happen so slowly that stars appear almost eternal. Civilizations rise and fall, while stars continue their gradual evolution, unhurried and steady. This contrast can be soothing, reminding us that not everything needs to move at our pace. Astronomers study these changes using powerful telescopes and careful measurements. By observing star clusters, where many stars formed at the same time but with different masses, scientists can piece together the life stories of stars. These observations support models of stellar evolution that have been refined over decades of research. In star clusters, it is common to see stars at many different stages of life at once. Some remain on the main sequence, while others have become giants or supergiants. Together, they form a living timeline of stellar development. As you relax, imagine a star slowly expanding, glowing warmly, and continuing its journey through time. There is no urgency, no struggle, only a quiet progression guided by gravity and energy. As we continue drifting through the quiet universe, we now arrive at one of the most peaceful yet fascinating chapters in the life of a star. How stars come to the end of their long journeys. These endings are not sudden for most stars. They unfold slowly, following the same calm rhythm that has guided them since birth. Let's begin with stars similar in size to our Sun. After spending time as a red giant, these stars eventually run out of fuel for further fusion in their cores. Once helium fusion slows and stops, the star can no longer support its expanded outer layers. Gravity begins to gently pull those layers away from the core. The star sheds its outer layers into space, forming what astronomers call a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers simply thought their round shapes resembled distant worlds when viewed through small telescopes. These glowing shells of gas drift outwards slowly, illuminated by the hot core left behind. The colors can be soft greens, pale blues, and gentle reds, depending on the elements present. Oxygen, hydrogen, and nitrogen all contribute to this quiet, cosmic display. At the center remains a white dwarf, the dense core of the original star. A white dwarf is incredibly compact, often containing about the mass of the Sun, squeezed into a volume similar to Earth. Yet, despite its density, it no longer produces energy through fusion. It simply glows with leftover heat. Over billions of years, a white dwarf cools gradually, fading into darkness. This final stage is called a black dwarf, though none exist yet, because the universe is not old enough for white dwarfs to cool completely. These stellar remnants remind us how long cosmic timescales truly are. This gentle ending reflects a broader theme in astronomy. Not all dramatic moments involve explosions or sudden change. Many of the universe's most important processes happen quietly, almost unnoticed. Now, let's turn our attention to massive stars, whose endings are far more energetic. These stars burn through their fuel quickly, living fast and shining brightly. When fusion reaches iron in their cores, the process can no longer produce energy. Iron marks the limit where fusion stops giving back more energy than it consumes. When this happens, gravity wins almost instantly. The core collapses in a fraction of a second, compressing matter to extreme densities. The outer layers rebound off this collapsing core, resulting in a supernova explosion. A supernova is one of the most powerful events in the universe. For a brief time, a single star can outshine an entire galaxy. Yet even this incredible explosion follows predictable physical laws, unfolding as part of the natural order of the cosmos. Supernovae are essential to the story of life. They create and scatter heavy elements like gold, silver, and uranium into space. These elements later become part of planets, oceans, technologies, and even human bodies. In a very real sense, the atoms within us were once forged in dying stars. After the explosion, what remains depends on the star's original mass. Some cores collapse into neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons on Earth. Neutron stars spin rapidly and can emit beams of radiation, becoming pulsars that flash rhythmically through space. If the star was massive enough, the core collapses even further, forming a black hole. Despite their mysterious reputation, black holes form through well-understood physical processes. They represent regions where gravity becomes so strong that not even light can escape. Even black holes are not chaotic destroyers. They follow clear rules, interacting with their surroundings in structured ways. Material spiraling into a black hole forms glowing disks, releasing energy that astronomers can detect from millions of light years away. Throughout these endings, stars continue to shape galaxies. Supernova explosions trigger new waves of star formation, compressing nearby gas clouds. White dwarfs and neutron stars contribute to the dynamic balance of stellar populations. Black holes anchor galaxies, influencing the motion of countless stars. From a broader perspective, stellar death is not an end, but a transformation. Matter is recycled, energy is redistributed, and the universe moves forward without waste. As you rest, imagine this cycle repeating endlessly across space. Stars are born, shine, change, and gently pass on their material to the next generation. There is no hurry, no final stop, only a continuous flow. This slow, meaningful rhythm is part of what makes astronomy so comforting. It reminds us that even endings have purpose and beauty. As we continue floating through the calm expanse of space, our attention now turns from individual stars to the gentle communities they form together. Stars are rarely born alone. Instead, they emerge in groups, shaped by shared origins and connected by gravity. Much like quiet neighborhoods scattered across a vast cosmic landscape. Most stars begin their lives inside giant molecular clouds, enormous regions of gas and dust drifting through galaxies. When portions of these clouds collapse, they often form dozens, hundreds, or even thousands of stars at roughly the same time. These siblings remain loosely connected, at least for a while, forming what astronomers call star clusters. One of the most peaceful types of stellar groupings is the open cluster. Open clusters contain anywhere from a few dozen to several thousand stars. They are often young, bright, and scattered across spiral arms of galaxies like our Milky Way. The stars within an open cluster share similar ages and chemical compositions, making them valuable natural laboratories for astronomy and education. The famous Pleiades cluster, sometimes called the Seven Sisters, is one of the closest and most easily visible open clusters from Earth. It has been known since ancient times and appears in myths, calendars, and navigation traditions across many cultures. This connection between science and human history highlights how stars have guided both curiosity and civilization. Open clusters are not permanent. Over hundreds of millions of years, gravitational interactions with nearby stars and gas clouds gradually pull them apart. Their stars drift away, becoming part of the galaxy's general population. Even as these clusters dissolve, their stars continue orbiting the galactic center, carrying with them the quiet memory of their shared beginning. In contrast, globular clusters are ancient and tightly bound. These spherical collections can contain hundreds of thousands or even millions of stars packed closely together. Many globular clusters formed during the earliest stages of galaxy formation, making them some of the oldest known structures in the universe. Globular clusters orbit the outer regions of galaxies, including the Milky Way. Their stars are typically low in heavy elements, reflecting a time when the universe had not yet been enriched by generations of supernova explosions. Studying these clusters helps astronomers understand the early economy of matter and energy in the cosmos. Despite their age, globular clusters remain remarkably stable. Their dense gravity keeps stars bound for billions of years, creating environments where stellar interactions are more frequent. In these crowded conditions, unusual stars can form, including blue stragglers that appear younger and brighter than their neighbors. Star clusters also play a role in shaping galaxies themselves. By tracing their positions, motions, and compositions, astronomers map the structure and history of galaxies. This work combines technology, mathematics, and observation, reflecting the collaborative nature of modern science. Beyond clusters, stars organize into larger neighborhoods within galaxies. Spiral arms, like those in the Milky Way, are regions of higher star density. They act as star-forming zones where gas clouds compress and collapse more readily. As galaxies rotate, stars drift in and out of these arms, participating in cycles of creation that span billions of years. Our own Sun resides in a relatively quiet region of the Milky Way, far from the crowded center. This stable environment may have contributed to the long-term development of life on Earth. In this sense, astronomy connects directly to questions of biology, ecology, and the conditions that support complex systems. Galactic neighborhoods vary widely. Some regions are bustling with star formation, glowing with nebulae and young stars. Others are calm and ancient, populated by older stars, moving in slow, predictable orbits. This diversity mirrors patterns seen in nature on Earth, from dense forests to open plains. Galaxies themselves gather into clusters and superclusters, forming immense cosmic networks. Yet, even at these scales, gravity guides movement gently and predictably. Nothing rushes. Everything unfolds at its own pace. As you rest, Imagine stars drifting together in clusters, orbiting quietly within galaxies, each following paths set long ago. There is comfort in this order, in knowing that even across unimaginable distances, the universe remains structured and serene. As we drift gently onward, the focus slowly shifts from stars themselves to the quieter companions that often surround them. Around many stars, unseen at first glance, are worlds in motion. These planets move along steady paths, shaped by gravity, time, and delicate balance. Together, stars and planets form systems that echo the calm rhythms found throughout nature. For much of human history, stars were thought to be solitary lights. Only recently has modern astronomy revealed that planets are common, not rare. Today, scientists estimate that most stars in the Milky Way host at least one planet. This discovery reshaped education, science, and our understanding of the universe's abundance. Planets form from disks of gas and dust that circle young stars. These protoplanetary disks resemble flattened rings, slowly rotating as particles collide and stick together. Over millions of years, small grains grow into rocks, then into planet-sized bodies. This process is gradual, patient, and remarkably efficient. Different types of planets emerge depending on distance from the star and available materials. Close to the star, where temperatures are higher, rocky planets tend to form. Farther out, where ices can survive, gas giants and icy worlds take shape. This pattern appears across many planetary systems, showing that physics creates order even in vast space. Our own solar system reflects this structure. Mercury, Venus, Earth, and Mars are rocky worlds close to the Sun. Beyond them lie gas giants like Jupiter and Saturn, followed by icy planets and distant objects. This layout is not unique, but it offers a familiar example of cosmic design. Some planets orbit stars very different from our Sun. Red dwarf stars, smaller and cooler, often host planets that orbit much closer in. These worlds may be tidally locked, with one side always facing the star, creating permanent day and night regions. Though unusual, such planets expand our understanding of habitability and climate. Astronomers detect planets using subtle methods. One common technique observes tiny dips in a star's brightness as a planet passes in front of it. Another measures the star's slight wobble caused by gravitational pull. These methods rely on precision technology, patience, and careful analysis. Thousands of confirmed exoplanets have now been catalogued, ranging from scorching lava worlds to cold gas giants drifting far from their stars. Some planets are larger than Jupiter, yet lighter than expected. Others are dense and compact, with compositions unlike anything found nearby. Among these discoveries are planets located in what scientists call the habitable zone. This is the region around a star where temperatures could allow liquid water to exist on a planet's surface. Water, essential for life as we know it, makes these zones especially intriguing. However, habitability depends on many factors: atmosphere, magnetic field, geological activity, and stellar behavior all play roles. A calm, stable star increases the chances for long-term planetary environments. In this way, stellar science connects directly to biology, chemistry, and the search for life. Stars influence their planets through light, heat, and stellar winds. Over time, intense radiation can strip atmospheres or alter surface conditions. Younger stars tend to be more active, while older stars often settle into quieter phases. This evolution affects the planets that orbit them. Planets, in turn, can affect their stars. Large planets exert gravitational forces that shapes stellar motion. In some systems, planets migrate inward or outward over time, reshaping the architecture of the entire system. These interactions highlight the dynamic nature of cosmic neighborhoods. Asteroid belts and comet clouds form from leftover material, creating reservoirs of icy objects. Occasionally, these objects travel inward, delivering water and organic compounds to inner planets. Such events may have played a role in Earth's early history. Looking outward, astronomers see young stars surrounded by glowing disks, evidence that planet formation is ongoing throughout the galaxy. Each disk represents potential worlds still in the making, quietly assembling over millions of years. This abundance of planetary systems changes how we view the universe. Rather than empty space punctuated by rare oases, the cosmos appears rich with structure, diversity, and possibility. It invites curiosity, wonder, without noise. As you relax, imagine planets tracing gentle arcs around their stars, moving in silence and balance. There is no rush, no conflict, only motion guided by gravity and time. As we continue, the universe gently shifts its focus from motion to time. Stars are not static lights. They are travelers through deep ages, living out long and carefully balanced lives. Each star follows a path shaped by mass, temperature, and gravity, unfolding slowly across millions or even billions of years. A star's life begins in calm darkness. Vast clouds of gas and dust, called nebulae, drift quietly through space. Over time, gravity gathers denser regions within these clouds, pulling material inward. As the cloud contracts, it warms, growing brighter and more concentrated. Eventually, a new star is born. When nuclear fusion ignites at a star's core, hydrogen atoms begin combining to form helium. This process releases energy, creating the steady light and warmth that define a star's main phase of life. For most stars, this stage lasts longer than any other, providing stability and predictability. Our Sun is currently in this main phase, known as the main sequence. It has been shining steadily for over 4 billion years and is expected to continue for billions more. This reliability has allowed life, climate, and ecosystems to develop on Earth over immense stretches of time. The length of a star's life depends largely on its mass. Smaller stars burn fuel slowly and carefully, conserving energy like a quiet lamp. Red dwarf stars, the most common in the galaxy, can shine for trillions of years. Their longevity makes them some of the universe's most enduring structures. Larger stars live faster, brighter lives. They burn through their fuel quickly, shining intensely but briefly. Though spectacular, their lifespans may last only a few million years. In cosmic terms, they blaze like brief flares against the darkness. As stars age, changes begin at their core. When hydrogen runs low, the balance between gravity and outward energy shifts. The star expands, cools, or contracts depending on its size. These changes are slow and graceful, unfolding over immense spans of time. Medium-sized stars, like the Sun, eventually become red giants. Their outer layers expand outward, cooling as they grow larger. During this phase, stars may engulf nearby planets or alter their environments significantly. Despite the drama, the process remains quiet and gradual. Eventually, stars shed their outer layers, releasing gas into space. These materials form glowing shells called planetary nebulae, enriching the surrounding region with heavier elements. The remaining core becomes a white dwarf, a dense, dim object, slowly cooling over time. White dwarfs no longer produce energy through fusion, but they continue to glow faintly from residual heat. Over trillions of years, they cool further, becoming darker and quieter. Though small, they represent the final resting state for many stars. Massive stars follow a different path. When their fuel runs out, gravity overwhelms them more suddenly. The core collapses, triggering a powerful explosion known as a supernova. For a brief moment, the star may outshine entire galaxies. These explosions scatter heavy elements across space, contributing to the formation of new stars, planets, and even life. Elements like iron, gold, and oxygen originate in stellar cores and supernova, linking every atom in our bodies to ancient stars. What remains after a supernova depends on the star's mass. Some leave behind neutron stars, incredibly dense objects spinning rapidly and emitting beams of radiation. Others collapse further into black holes, regions where gravity becomes overwhelming. Despite their dramatic ends, massive stars play essential roles in cosmic recycling. Their brief lives seed galaxies with the materials needed for complexity, chemistry, and future generations of stars. Across the Milky Way, stars exist at every stage of life. Some are newly born, still wrapped in glowing clouds. Others are mature and steady. Many are ancient, nearing the end of their luminous journeys. Together, they form a balanced and ongoing cycle. Blue stars are typically hotter and younger, while red stars are cooler or more evolved. These clues allow scientists to read stellar history from light alone. This slow evolution gives the universe its gentle rhythm. Nothing happens suddenly on a human timescale. Stars change patiently, reminding us that time itself can be expansive and calm. As you listen, imagine a star quietly aging. Its light, steady and reassuring. It does not hurry toward its future. It simply follows the path set by physics and balance. As the night continues, the story of stars gently widens from individual lives to shared spaces. Stars are rarely alone. Most are born in groups, drifting together through space like quiet communities, connected by gravity and shared origin. When stars form inside large clouds of gas and dust, they often emerge together. These stellar nurseries give rise to clusters where dozens, hundreds, or even millions of stars begin their lives side by side. Though they may eventually drift apart, their earliest moments are shared. Open clusters are among the most familiar star families. They contain a few hundred stars loosely bound by gravity. These clusters often shine brightly against the dark sky, their stars young, blue, and energetic. Over time, gravitational interactions slowly pull them apart. The Pleiades, sometimes called the Seven Sisters, is a well-known open cluster visible to the naked eye. Its stars are relatively young, only about 100 million years old. They glow with a soft, blue light, surrounded by faint clouds of dust reflecting their brilliance. Open clusters are important to astronomy because their stars form at the same time and distance. This allows scientists to study how stars evolve by comparing differences caused only by mass. In this way, clusters become natural laboratories for stellar science and education. Globular clusters are older and more tightly bound. These dense, spherical collections can contain hundreds of thousands or even millions of stars. They orbit the outer regions of galaxies, including the Milky Way, like ancient guardians. The stars within globular clusters are among the oldest known, often more than 10 billion years old. Their warm yellow and red colors reflect long lives and steady energy output. These clusters preserve a snapshot of the early universe. Because of their density, globular clusters are calm yet crowded places. Stars pass relatively close to one another, but space is still vast enough to prevent frequent collisions. Gravity maintains a slow, graceful balance among them. Beyond clusters, stars organize themselves into galaxies. A galaxy is a massive system of stars, gas, dust, and dark matter bound together by gravity. The Milky Way, our home galaxy, contains hundreds of billions of stars. The Milky Way is a spiral galaxy with sweeping arms extending from a bright central core. These arms contain gas clouds, young stars, and regions of active star formation. Our Sun resides in one of these arms, far from the crowded center. Galaxies come in many shapes. Some are elliptical, appearing smooth and rounded, filled mostly with older stars. Others are irregular, lacking defined structure and shaped by gravitational interactions or past collisions. Galaxies often gather into groups and clusters, forming vast cosmic neighborhoods. The local group, which includes the Milky Way and Andromeda galaxies, contains dozens of smaller galaxies drifting together through space. Over immense timescales, galaxies interact and merge. These events unfold slowly, taking hundreds of millions of years. When galaxies merge, stars usually pass by one another safely, while gas clouds collide and trigger new star formation. These galactic interactions shape the evolution of the universe. They redistribute matter, fuel star birth, and influence the structure of cosmic space. Even our Milky Way is on a gentle collision course with Andromeda, expected to merge billions of years from now. Within galaxies, stars orbit the center, moving in graceful paths governed by gravity. These orbits take millions of years to complete. The Sun, for example, completes one galactic orbit approximately every 225 million years. This slow movement reminds us how vast space truly is. Even traveling at tremendous speeds, stars require immense time to journey across their galactic homes. The night sky we see today is a snapshot of many moments layered together. Star clusters gradually dissolve as gravitational influences pull stars away. Over time, their members become part of the broader galaxy, blending into its luminous population. Though separated, they retain shared origins. Astronomers trace these connections by studying stellar motion and composition. Stars, born together, share chemical signatures, allowing scientists to reconstruct ancient star families long after they disperse. In this way, the universe remembers its past. Patterns persist quietly through motion and light, telling stories across billions of years. As you rest, imagine stars drifting gently through their galactic neighborhoods. Never rushed, always guided by gravity's calm pull. They belong to something larger, just as we do. As the quiet night drifts onward, our focus softens from stars themselves to what often surrounds them. Many stars are not alone in the cosmic sense. They host planets, moons, rings, and debris, forming complete systems that move in slow, graceful harmony. Planets form from disks of gas and dust left over after a star's birth. These protoplanetary disks flatten into spinning circles around young stars. Over time, tiny particles collide, stick together, and gradually build larger bodies. Within these disks, different regions create different worlds. Close to the star, heat allows only rock and metal to remain solid, forming terrestrial planets. Farther out, colder temperatures allow ice and gas to accumulate, creating giant planets and icy bodies. Our solar system is just one example among billions. Astronomers have discovered thousands of exoplanets orbiting distant stars, revealing an astonishing variety of planetary systems. Some planets are larger than Jupiter, while others are smaller than Earth. Many stars host planets that orbit extremely close, completing a year in just a few days. These worlds experience intense heat and tidal forces, shaping extreme environments that challenge our understanding of planetary science. Other planets orbit at distances where temperatures allow liquid water to exist on their surfaces. This region, known as the habitable zone, varies depending on the star's size and brightness. It is one of many factors scientists consider when studying planetary habitability. Stars play a central role in shaping the climates of their planets. A star's brightness, temperature, and stability influence atmospheric chemistry, weather patterns, and long-term climate evolution. Smaller stars, such as red dwarfs, burn fuel slowly and live for trillions of years. Their longevity provides extended opportunities for planetary development, though their energetic flares can pose challenges for nearby worlds. Larger stars burn hotter and brighter, but live shorter lives. Their planets experience intense radiation and shorter windows for stable conditions. These differences highlight the delicate balance required for planetary environments to persist. Planetary systems are not static. Over time, gravitational interactions shift orbits, migrate planets, and sometimes eject bodies entirely. These slow changes shape the architecture of each system. Moons add further complexity. Many planets host natural satellites that influence tides, stabilize axial tilt, and create unique environments. Earth's moon, for example, plays a crucial role in regulating our planet's climate and seasons. Rings of dust and ice often surround young stars, and mature planets alike. These rings reflect ongoing processes of formation and evolution, providing clues about the history of their systems. Asteroid belts and comet reservoirs are also common. These regions contain remnants of planetary formation, preserved as cosmic archives. When comets approach a star, their icy surfaces release gas and dust, creating glowing tails. The interaction between stars and their surrounding material generates beauty as well as balance. Stellar winds gently shape planetary atmospheres, while radiation drives chemical reactions that build complexity. In some systems, stars exist in pairs or groups, known as binary or multiple star systems. Planets can orbit one star or both, creating fascinating orbital patterns rarely seen in our own solar system. Binary stars are common in the universe. Their gravitational dance influences planet formation and stability, offering insight into the diversity of cosmic architecture. Planetary systems also evolve through dramatic events. Collisions between planets, moons, or asteroids can reshape worlds, alter climates, and even create moons. These processes unfold slowly, measured in millions of years. Change in the cosmos is gentle and patient, guided by gravity and time, rather than sudden motion. Observing distant planetary systems allows scientists to understand how common certain conditions may be. Each discovery expands our understanding of where life-friendly environments might arise. Space exploration technology continues to improve, enabling detailed study of exoplanet atmospheres. Scientists search for chemical signatures that hint at oceans, clouds, or biological activity. These efforts connect astronomy with education, technology, and global collaboration. The quest to understand planetary systems reflects humanity's curiosity and shared desire to explore. As you rest, imagine countless stars hosting quiet worlds, each following steady paths through space. Their motions are calm, repetitive, and balanced, like a cosmic lullaby. As the night grows deeper and quieter, we turn our attention to rhythm. Stars do not merely shine. They set the tempo of entire systems. Around them, time unfolds in repeating patterns that feel steady, predictable, and deeply calming. On planets, the passage of time is often defined by the motion around a star. A single orbit becomes a year, a slow and graceful loop shaped by gravity and momentum. Each year marks a return to familiar positions, like a cosmic heartbeat. Rotation adds another layer of rhythm. As planets spin, they experience day and night, light and darkness, cycling gently beneath the glow of their star. This regular alternation influences temperature, weather, and biological activity. The tilt of a planet's axis creates seasons. As a world leans toward or away from its star during its orbit, sunlight shifts across its surface. These changes bring cycles of warmth and coolness, growth and rest. Earth's seasons are a familiar example, but throughout the universe, seasons vary widely. Some planets experience mild changes, while others endure extreme variations lasting years or even decades. Stars themselves also follow cycles. Many stars exhibit magnetic activity that rises and falls over time. These cycles influence stellar brightness, radiation, and the behavior of stellar winds. Our Sun, has an approximately 11-year activity cycle. During periods of high activity, sunspots increase and solar flares become more frequent. During quieter phases, the sun appears calmer and more uniform. These cycles affect space weather, subtly influencing planetary atmospheres and magnetic fields. They remind us that even seemingly constant stars are dynamic, living systems. Longer-term, stellar cycles shape entire eras. As stars age, their energy output changes gradually, influencing the long-term climates. On cosmic scales, rhythm extends beyond individual systems. Galaxies rotate, stars orbit galactic centers, and clusters drift slowly through space. These motions are so vast and slow that they feel almost timeless. Within galaxies, spiral arms rotate like gentle waves. Stars pass through these arms over millions of years, encountering regions rich in gas and dust where new stars are born. Time in the universe unfolds at many speeds. Some processes happen quickly, like stellar flares lasting minutes. Others take billions of years, like the slow cooling of a star after its fuel is exhausted. Astronomy teaches us patience. To understand stars, scientists observe patterns over long periods, building knowledge slowly, generation by generation. Calendars, clocks, and navigation systems on Earth all trace their origins to the stars. Ancient cultures used stellar cycles to track seasons, guide travel, and plan agriculture. Even today, precise measurements of stellar motion support modern technology. Satellite systems, global communication, and navigation rely on an understanding of Earth's position in space. Timekeeping based on atomic clocks now surpasses stellar observation in precision. Yet, it is still tied to Earth's rotation and orbit around the Sun. Some stars pulsate rhythmically, expanding and contracting in regular cycles. These variable stars change brightness predictably, serving as cosmic metronomes. Keyfied variable stars are especially important. Their pulsation periods reveal their true brightness, allowing astronomers to measure distances across the galaxy and beyond. These rhythmic stars have helped map the universe, linking time, light, and distance into a unified understanding of space. Other stars rotate so rapidly that their shapes flatten slightly. Their rotation affects magnetic fields and surface temperature distribution, creating subtle variations in brightness. Planets also influence stellar rhythm. Massive planets can cause stars to wobble gently, revealing their presence through precise measurements of motion. This stellar wobble method has been one of the most successful techniques for discovering exoplanets, demonstrating the delicate gravitational dance between stars and their worlds. Cosmic cycles bring reassurance. No matter how vast or complex the universe becomes, it operates through repeating patterns that feel steady and reliable. As you breathe slowly, imagine these cycles continuing far beyond awareness. Stars rise and fall in brightness, planets circle faithfully, galaxies turn with quiet persistence. As the universe continues its calm and unhurried motion, we now turn to starlight itself. Light is the primary language of the cosmos, a gentle messenger that carries stories from distant stars across unimaginable distances. When a star shines, it sends energy outward in all directions. These light waves travel through the quiet darkness of space, sometimes for millions or even billions of years before reaching another world. Starlight moves at a constant speed, known as the speed of light. Even at this incredible velocity, distances in space are so vast that light takes time to arrive. When we observe a star, we are seeing it as it was in the past. Some stars visible in the night sky no longer exist. Their light continues to drift through space, arriving long after the star itself has changed or faded away. Light carries detailed information. Its color, brightness, and subtle patterns reveal a star's temperature, size, age, and chemical composition. By spreading starlight into a spectrum, astronomers can identify specific elements present in a star. Each element leaves a unique signature, like a cosmic fingerprint. Hydrogen and helium dominate most stars, but traces of heavier elements such as carbon, oxygen, and iron appear as well. These elements tell the story of previous generations of stars. Light also reveals motion. As a star moves toward or away from us, its light shifts slightly in color. This Doppler effect allows scientists to measure stellar velocities with remarkable precision. Through these measurements, astronomers map the motion of stars within galaxies, uncovering patterns of rotation and migration. Some stars emit light unevenly, flickering or pulsing over time. These variations provide insight into internal processes such as pressure changes or energy flow within the star. Other forms of radiation travel alongside visible light. Stars emit infrared warmth, ultraviolet energy, and even X-rays, each revealing different layers of stellar behavior. Infrared light penetrates dust clouds, allowing astronomers to see stars forming deep within nebulae. Ultraviolet radiation highlights hot, energetic regions around young stars. X-rays often signal extreme environments, such as rapidly rotating stars or systems where matter falls onto dense stellar remnants. Together, these wavelengths create a complete picture of stellar life, like layers of meaning within a calm and complex conversation. Starlight interacts gently with space along its journey. Dust particles scatter light, creating soft glows and colorful clouds that shape the beauty of galaxies. Sometimes, light bends as it passes massive objects, a phenomenon called gravitational lensing. This effect magnifies distant stars and galaxies, allowing us to see farther into space. Light also carries clues about the expansion of the universe. Distant galaxies show a redshift in their light, indicating they are moving away from us as space itself stretches. This quiet stretching of space happens everywhere, slowly and evenly, shaping the large-scale structure of the cosmos. Stars communicate not only through light, but also through particles. Stellar winds stream outward, carrying charged particles into surrounding space. These winds interact with planetary magnetic fields, creating auroras and shaping atmospheric boundaries. Occasionally, stars send more dramatic messages. Explosions, flares, and bursts release sudden waves of energy detectable across vast distances. Despite their intensity, these events remain rare and brief compared to the long, calm lifespans of most stars. Human technology listens carefully to these stellar messages. Telescopes on Earth and in space collect faint signals, translating them into images and data. Through this quiet observation, knowledge grows steadily. Each photon captured adds another detail to our understanding of the universe. Starlight connects everything. The light that reaches your eyes tonight began its journey long before human history, carrying the calm persistence of the cosmos. As the night sky remains still and expansive, we now turn our attention to how stars rarely exist entirely alone. Across the universe, stars form families, drifting together through space in gentle, long-lasting communities. Most stars are born within groups. These groups emerge from vast clouds of gas and dust, where gravity quietly gathers material into countless glowing points of light. When a stellar nursery produces many stars at once, the result is often a star cluster. These clusters remain loosely bound by gravity, moving together through their galaxy. There are two main types of star clusters: open clusters and globular clusters. Each type offers a different view into stellar life and cosmic history. Open clusters contain a few dozen to several thousand stars. They are usually young, forming in the spiral arms of galaxies where gas and dust are abundant. These clusters appear scattered and airy, with stars spread out in gentle arrangements. Over time, gravitational interactions cause many open clusters to drift apart. Despite their temporary nature, open clusters provide valuable insight into early stellar development. Because their stars share a common origin, they have similar ages and compositions. The famous Pleiades cluster, sometimes called the Seven Sisters, is one such open cluster visible to the naked eye. Its soft blue stars shimmer gently in the night sky. Globular clusters, by contrast, are ancient and densely packed. They contain hundreds of thousands or even millions of stars tightly bound together. These clusters orbit the outer regions of galaxies, forming spherical halos that surround galactic disks. Globular clusters are among the oldest structures in the universe. Many formed shortly after galaxies themselves, preserving clues about early cosmic conditions. Their stars are typically low in heavy elements, indicating they formed before multiple generations of stellar recycling enriched the universe. Inside a globular cluster, stars move in intricate patterns, weaving through one another in slow and graceful orbits. Despite their density, collisions between stars remain rare due to the vast distances separating them. Star associations represent another type of stellar grouping. These are loose collections of stars that form together but are not gravitationally bound. Over time, associations gradually disperse, their stars blending into the broader galaxy. Binary and multiple star systems also form a kind of family. Many stars orbit a partner, sharing gravitational bonds that shape their evolution. In some systems, stars exchange material, influencing each other's brightness, temperature, and lifespan. Binary stars play a key role in astronomy. Their interactions allow scientists to measure stellar masses with remarkable accuracy. At larger scales, stars gather into spiral arms, bars, and galactic cores, forming vast stellar neighborhoods within galaxies. These neighborhoods influence star formation rates, chemical composition, and overall galactic structure. Our own sun belongs to a quiet region of the Milky Way, far from crowded clusters and intense stellar activity. Even so, the sun likely formed alongside sibling stars that have since drifted away, scattered throughout the galaxy. Astronomers search for these lost siblings by comparing chemical signatures, hoping to reconstruct the sun's original family. Galaxies themselves form communities. Groups and clusters of galaxies interact through gravity, shaping the large-scale structure of the universe. Within these enormous systems, star formation ebbs and flows, influenced by galactic mergers and cosmic environment. Despite the complexity, star families evolve slowly, following predictable rhythms guided by gravity and time. Each cluster, association, and system represents a chapter in the ongoing story of the cosmos. As we rest with this thought, imagine countless stars drifting together, bound by gentle forces across the vastness of space. As the universe remains calm and unhurried, we now drift toward the quiet relationship between stars and the worlds that circle them. Every planet, moon, and ring system begins its story under the influence of a star's gentle gravity and warming light. Stars are the architects of planetary systems. When a star forms, leftover gas and dust flatten into a rotating disk that surrounds the newborn light. Within this disk, particles slowly collide, stick together, and grow. Over long spans of time, these tiny grains become rocks, then boulders, and eventually full-sized planets. This process unfolds slowly, like a patient cosmic lullaby. The position of a planet within its star system shapes its destiny. Distance determines temperature, surface conditions, and the presence of liquid water. Astronomers describe a region called the habitable zone, where temperatures may allow water to remain liquid on a planet's surface. This gentle balance depends on a star's brightness and size. Smaller, cooler stars have closer, habitable zones, while larger stars require planets to orbit farther away. Our Sun's habitable zone includes Earth, where oceans have remained stable for billions of years. Starlight also drives planetary climates. The energy received from a star influences winds, weather patterns, and seasonal cycles. On Earth, the tilt of our planet, combined with the Sun's steady output, creates the rhythm of seasons, shaping ecosystems and cultures alike. Stars emit more than visible light. Ultraviolet radiation, solar winds, and charged particles interact with planetary atmospheres. Magnetic fields act as shields, protecting planets from harmful radiation. Earth's magnetic field deflects much of the Sun's energetic output, preserving our atmosphere. Without such protection, atmospheres can slowly erode, as seen on Mars, where solar winds stripped away much of its early air. Some stars are more active than others. Young stars often flare and emit bursts of radiation that can challenge nearby planets. Red dwarf stars, though long-lived and common, frequently release powerful flares that bathe close-orbiting planets in energy. Yet, even in these environments, scientists consider the possibility that life could adapt beneath surfaces or within oceans. Stars also influence planetary chemistry. Their radiation drives chemical reactions that shape atmospheres and surface conditions. Complex molecules can form in protoplanetary disks long before planets fully assemble, seeding young worlds with the building blocks of life. As stars age, their changing brightness affects orbiting planets. Gradual increases in stellar output can warm planets over billions of years. Far in the future, the Sun will expand into a red giant, altering or ending the habitability of inner planets. Binary star systems create even more complex planetary environments. Some planets orbit one star, while others circle both in wide, graceful paths. These systems experience shifting patterns of light and shadow, creating dramatic skies unlike anything on Earth. Observations show that planets are common throughout the galaxy. Nearly every star likely hosts at least one world. Some planets are rocky, others gaseous, and many fall somewhere in between, expanding our understanding of planetary diversity. Stars guide planetary orbits through gravity, maintaining stability or, at times, triggering dramatic migrations. In young systems, planets may move inward or outward, reshaping the architecture of their celestial neighborhoods. Stars also provide the energy that sustains potential biospheres. Photosynthesis, weather cycles, and ecological balance depend on steady, stellar light. From a quiet cosmic perspective, stars act as caretakers, shaping worlds through consistent presence rather than sudden force. As we gently pause here, imagine distant planets bathed in soft starlight, slowly turning through long nights and peaceful days. Now, as our journey gently nears its end, we drift into the far future, a future so distant that even time itself seems to slow and soften. Here, we explore what awaits and the universe as a whole in a calm and unhurried way. Stars, though brilliant and powerful, are not eternal. Each one follows a slow and predictable path shaped by mass, gravity, and time. Some stars will shine for only millions of years, while others glow steadily for trillions. The smallest stars, red dwarfs, are the universe's great long-distance travelers. They burn their fuel so slowly that none have yet reached the end of their lives. Many will still be shining long after larger stars have faded. Larger stars live faster and more dramatic lives. They swell, shed their outer layers, and leave behind glowing nebulae that drift quietly through space. These clouds of gas become raw material for future generations of stars. White dwarfs, the remnants of sun-like stars, cool slowly over unimaginable spans of time. Eventually, they will fade into cold, dark objects known as black dwarfs, though the universe is not yet old enough for any to exist. Neutron stars and black holes remain as dense echoes of massive stars. They persist quietly, influencing their surroundings through gravity rather than light. Galaxies themselves evolve. Over billions of years, they merge, stretch, and reshape. Our Milky Way is slowly moving toward the Andromeda Galaxy, and in several billion years, the two will blend into one vast, calm structure. As star formation gradually slows, galaxies will grow darker. Fewer new stars will ignite, and the night skies of distant planets will contain fewer points of light. Eventually, the universe may enter an era sometimes called the stellar twilight, when most stars have exhausted their fuel. After that comes a time of deep cosmic quiet. With no new stars forming, the universe becomes dominated by faint remnants and drifting matter. Black holes may be among the last active objects, slowly evaporating through a process known as Hawking radiation over timescales far beyond human comprehension. Even protons themselves may decay, if certain theories are correct, leading matter to slowly dissolve back into energy. What remains is a universe that is vast, cold, and peaceful, a place of long darkness and infinite stillness. Yet this future is not something to fear. It represents completion rather than loss, a natural settling after immense creativity. Everything we see today, stars, planets, galaxies, and life, is part of a temporary but meaningful chapter in cosmic history. The atoms in our bodies were once forged in stars, linking us forever to this larger story. As you rest now, remember that the light from distant stars began its journey millions of years ago, traveling quietly through space to reach your eyes. Even as you drift toward sleep, the universe continues its slow, steady rhythm, unchanged by hurry or worry. Stars rise and fade, galaxies turn, and time flows onward with gentle certainty. You are part of this vast unfolding, carried softly on a small planet beneath a quiet sky. Let your thoughts settle like starlight fading at dawn. Sleep well, and may the universe feel calm and close.